Okay, so in this section we're gonna try to predict the peak intensities for a single phase, and you can see the connections here to the mixed phase because we're basically able to use the similar expressions to be able to predict what a single phase pattern would look like. Previously, we talked about the structure factor and how that determines the relative peak intensity, or whether a peak will even exist. And so that is one factor that goes into excuse me, that is one factor that goes into determining peak intensity, but there are others as well. And so let's look at what those other factors are. So along with structure factor, we have multiplicity. So this is the multiplicity factor, and we give this a lowercase p. So this is the number of permutations of the HKL planes affects and how the number of permutations affects the probability that a given plane will be oriented for diffraction. So the more permutations we have of a HKL type of plane, the more likely it is going to be in the preferred orientation, meaning that it diffracts, and therefore the multiplicity factor goes up, and therefore we'd expect that the resulting higher p-value leads to a higher intensity. So this is one other factor along with structure factor. Also, the Lorentz polarization factor, or LP. So in this case, this has to do with angle. So we see that the intensities are relatively, so I'm just abbreviating it here, large. So the intensity is relatively large at low and high angles. And this is from geometric considerations. So basically, this accounts for the kind of geometry of the experiment and how that can affect the intensity. The other term is the temperature factor. So what we see is that the intensity decreases and the background scattering that we have increases with increasing temperature. So that's why we name it the temperature factor. But so this is just a relationship that's known with temperature, but also more importantly for us, because most of these experiments are done at room temperature, they're not done at high temperatures. So more importantly, the same relationship holds true for increasing angle. At a constant temperature. So it's got a confusing name because it's called the temperature factor, and we don't necessarily care about temperature, but it does tell us the same relationship that happens with increasing increasing temperature. Okay, so looking at these factors, we can now put together a relationship that's going to tell us about the intensity. So the integrated intensity of a diffraction peak can be calculated as the following equation. So we have intensity of the given peak is, let me rewrite this. Sorry about that. Intensity is equal to the absolute value of the structure factor for that given peak squared times the multiplicity factor times the Lorentz polarization factor. And again, note the expression here. It may look odd, but this should be the correct form of the equation. Take a look in your book, and I believe you'll find something different that doesn't match with the tabulated values. And lastly, we've got the temperature factor, which is this exponential term here. And so we don't calculate this. This is tabulated, or you can find this graphically in figure 2.27. So this is how we can determine the intensity for each peak, and this would allow us to predict what along with the 2 theta values and everything else we've done in terms of structure factor, what the overall integrated intensity of a diffraction peak would be. So this would allow us to predict a structure. So imagine we have 2 theta and intensity, and we want to sort of predict what that would be for a given material, like iron that is BCC. Well, we can determine the angles of the diffraction peak, right? We can determine where those angles are using Bragg's law and the allowable S values for BCC, but we don't know about the relative intensities here. So this expression applied to each of these peaks would allow us to figure out what these relative integrated intensities would be. And so that's the power of this expression for a single phase. All right, to wrap up this module, let's look at calculating one of these values just to get a sense for what they all are. So let's imagine that we're looking at a particular family of planes, and I want you to calculate, and I want you to find the multiplicity factor. And this is for the 001 and the 111 family of planes. And so this is in a cubic system. So see if you can kind of visualize the cubic structure and visualize these two families of planes, and see if you can come up with how many different permutations to give us the multiplicity factor, and we'll come back and we'll discuss. So we're back now. Let's look at the multiplicity factor. Let's start with the 001. So all multiplicity factor is the number of permutations for that specific family. So in cubic, X, Y, and Z are all the same, associated the same. So we can look at anything that's in the 001 type, which would be the same as 010, which is the same as 100. So we've got 3, but we also can do the negatives. So we can have bar 1 in any of those cases. And so this gives us 6 different. So we have 6 here for the 001 type. We can also run through the same logic looking at the different permutations of those values for 111, and if we do that, then we find that this is 8. So I'll leave that as an exercise for you, but I'll also mention that the multiplicity factors, you typically don't have to calculate them each time for a given type of HKL and for cubic or hexagonal. Those values are tabulated. So I've put a whole list of appendices from the Colody text so that you can do the homework and various assignments for the multiplicity, but it also has Lorentz polarization, the temperature factor. There's a lot of other information there that will help you in these sorts of questions.